And this last question was a great transition to our next talk, which will be about the Rubin Observatory LSST. So we will have two speakers. The first one is Chihway Chang, who is the Claire Booth Luce Assistant Professor in the Department of Astronomy and Astrophysics at U Chicago and a senior member of KICP, which I hear may have a 20-year anniversary coming up soon. Chihway got her PhD between 2007 and 2013 at KIPAC with Steve Kahn and Rafe Schindler. She's an expert in all things observational cosmology, galaxy surveys, and in particular, galaxy weak lensing, the analysis of small scales and baronic effects. And I think we will have a seamless transition to Phil Marshall after this, who is currently a senior staff scientist at KIPAC and was one of the very first generation of postdocs at KIPAC in 2003. He then returned in 2009 as a Kavli Fellow and then returned again in 2013 to join the staff permanently. So if you come here, you may never leave. He has been the Deputy Director of Operations of the Rubin Observatory, and his leadership led to the formation of the LSST desk, the Dark Energy Science Collaboration, for which he was the spokesperson 2017 to 2019. He's an expert on strong gravitational lensing as a probe of expansion and dark matter. So please take it away, Chihway. Thank you.
Is this on? Yeah, cool. Great. So thanks for the introduction, and thanks the organizer for putting this together. It's been extremely fun to see all the old friends and make new friends with all the people who came through in the 20 years of KIPAC. So Phil and I were tasked to talk about the Vera Rubin Observatory. We're going to talk a little bit about the history, what it's doing now, and we're going to zoom in on cosmology and weak lensing because that's what I'm familiar with, and highlight some of the people in KIPAC that has really contributed to the field. Right. Oh, I want to say a little bit. Okay, so this is arguably the first sketch of the optics of the Rubin telescope, which I stole from Tony Tyson, who he stole from Roger Angel. The thing I wanted to highlight is just when this happened. This is about 2001, so about also 20 years ago. Okay, so a little bit about your speakers today. I was trying to look through photos of Phil and me together, and I was not successful, so I went upstairs to the second floor kitchen, and I found this. So you can see Phil there and me there. 15 plus years ago, I think Risa was right that the resolution of photos were worse back then. But yeah, so this is a photo. So I was here as a PhD student in 2007 through 13. Phil was one of my main postdoc mentors. We worked together on various projects. And after that, we kind of crossed paths here and there. So it's really a pleasure and really exciting that we're giving this talk together today. Okay, so many of you probably heard of Rubin, and depending on your science, you would use it for different things. So you can study galaxies, large-scale structures, stars, dust, as we just heard about. But I think the thing I want people to keep in mind and throughout this talk is this is a generic survey. It's going to map the sky in various axes. And what is really going to come out that is exciting, we may not even know or be able to predict right now. And I think that's kind of a theme going on, but we know it's going to be exciting. This is a picture of the Rubin kind of telescope now on the summit, together with the auxiliary telescope on the ridge. If you go into the dome, you can see the telescope itself. It's very busy on the summit these days. Things are happening. We're practicing how to move giant mirrors onto the mount. We're practicing how to point the telescope here and there. So this, as you see it, is a very real structure, right? It's a telescope about to start. I'm going to walk you back very quickly in reverse chronological order to see how this came about and where KIPAC came in throughout the journey. Okay, so I'm going to play a video. It's going to go by really fast. It's about 50 seconds that encapsulates about like from 2011 to today, so like 10, 12 years. And it's going to start from kind of the first blast on the mountaintop to the Rubin telescope we see today. I won't talk, I just want you to absorb kind of the making of LSST. Okay, if this loads, that is. Okay, so that's a blast. And then we start building things. Okay, that's 2017. It went by fast. You can see we don't have a dome yet. There's still going to be snow falling into the dome. Now we're starting to add stuff on it. Okay, so this is more or less complete to 2020. Now we're going to put in the structure for the telescope. You can see the dome moving around. 2021. Okay, so this is about where it ends, and that's pretty much what you see if you go on the mountaintop today. Okay, so that went by very fast, but there was a long period of time before that where Rubin exists as an artist rendition that we all are very familiar with. So this is the cover of the science book that came out in 2009. Many of you might know. And there's many designs, many scientists trying to figure out how to design the telescope to do the science we want to do. You might also be very familiar with this picture, which is one of the artist renditions of the optical design of Rubin back then. You have the 3-mirror system that we all know and love these days. M1 and M3 are one single piece of glass. M2 is up there, it can bounce down, and then it goes into the camera looking down with the lenses. So this all happened before the first class. Obviously, it went through various reviews. It went through Astro 2010, many may remember. And I even wrote a thesis about it like that many years ago. So the title is Systematic Effects in Cosmic Shear Measurements for Future Ground-Based Optical Surveys, and that basically was referring to LSST. So obviously, I've been waiting for this thing to happen for a long time, but there's many who've been waiting for it much longer than I did. Okay, so if you were paying attention, you would realize that this optical system is slightly different from the draft that, the sketch that I showed in the first slide. Obviously, many good engineers went and tried to implement this, where it came from, basically Roger Angel was a scientist at Arizona who communicated this idea to Tony Tyson over a phone call, later sketched this idea on a piece of, I forgot, like a projector sheet in Aspen 2001. So the idea is, if you want a very fast optics in order to map a big chunk of the sky in a short amount of time, you need the kind of the optical path to converge very quickly. But at the same time, you want to maintain a very homogeneous point spread function over the focal plane. You can't do it with one mirror. You can't do it with 2 mirrors. You have to do it with 3 mirrors. So that's kind of the initial idea, and it stuck. It went through all this process, and it took a long time to get to where we are at. But it's really amazing to appreciate that this actually came from such an incident where basically scientists talking and coming up with such an idea. Okay, we could go even further. Rubin, before it was called Rubin, it was called LSST, the Large Synoptic Survey Telescope, which many of you might remember. And before that, you can see down here, it was called the Dark Matter Telescope. So it was motivated by mapping dark matter. This thing that people were finding around the 70s, primarily kind of pioneered by Vera Rubin, looking at galaxy rotation curves. So really, the story has came full circle, right? Rubin discovered dark matter, motivated this whole thing. Now the telescope is named after her. And I think it's a really cool story to kind of think about. Okay, so that was kind of a quick history of Rubin. Now, throughout those 20 years, KIPAC has been in the center of a lot of this. I think Risa showed this at the beginning, 2003, when KIPAC first started. Roger was the director, Steve was the deputy director. Both of them had in mind that LSST is going to be one of the projects that we really want to take on here at KIPAC. Later, like the development of the camera, obviously you heard about that was done here. There's going to be a camera tour on Wednesday. You should go. This is one of the camera tours I went to in in March, where we saw the camera just being closed up. And in addition to that, there's a lot of activity here that is associated with DESC, the Dark Energy Science Collaboration that I think Manu mentioned. In fact, just in July or August, I don't remember anymore, we had a DESC collaboration meeting here that was just outside. You can see like hundreds of people happy and doing science with the kind of the expectation of LSST data coming in. Okay, so with that, the rest of my talk, I'm going to go through a quick kind of reminder of the survey I keep talking about, what it's going to do and what science it's motivating. Then we're going to go to a quick tour to understand how the survey operates and how we're actually taking this data. And the last bit, I'm going to talk about some of the science we're doing in DESC, focusing on weak lensing and highlighting some of the people at KIPAC. And this is another picture of the summit 2 months ago when it's snowing. Okay, so LSST must be the most clever renaming ever, going from Large Synoptic Survey Telescope to the Legacy Survey of Space and Time. Rubin, the one most important task of Rubin is to carry out this survey. And just to be pedantic, a survey means that we're scanning the sky, not looking at a particular interesting system, but just going on, scanning the sky, mapping everything that's out there. So we're a survey of space and time, meaning we're doing both axes. We don't not only want to map a lot of space, we also want the temporal kind of resolution to see things that are changing. Okay, so the first video I'm going to show here is kind of an idea of the space axes. So Rubin is going to map 18,000 square degrees, which is about a third of the sky in 6 filter bands. And it's going to do this very quickly because of this brilliant optical design. Here's showing kind of over one night how the scheduler is moving across the sky. On the right, you see basically the final footprint of LSST. You can't read this very well, but you can vaguely make out at a given patch, you have about hundreds of visits in a given patch. Okay, similarly, in the time axes, because we're taking this full sky map every 3 or so days, you actually can build up a very general movie of the sky over 10 years. So this is over the span of about 180 days, transient sky. Just you can see things being lit up. Can I do this again? Okay, maybe not. Or maybe I can do this. Okay, so the transient sky lighting up, all these stars dying and blowing up, and you can see them slowly also fading away. So this is what we're going to get with LSST, and it's revolutionary, it's unprecedented. We never had this kind of data before, and it's really exciting. Okay, that was a talk from Andy Connolly in a TED Talk. Okay, so really it's not only about mapping the sky, we're actually filming the sky. We're making a movie with all these dynamical things happening. And in the end, this is what we're going to get over 10 years. 20 billion galaxies, 17 billion stars, 10 million supernova, 6 million solar system objects. And all of this is by design motivated by the science topics over here. Understanding dark matter. So this also includes general cosmology, dark energy, and all of that. Cataloging the solar system. So understanding all these TNOs and comets that are going around. Mapping the Milky Way, understanding our galaxy, how the structure looks, the fine details of where the stars are, and then all these transients that we are not really sure how to characterize them currently or in a systematic way. There's a lot more to do there. That's why we're using the exploring kind of adjective there. Right, so just to come back to the theme, these are the scientific areas that motivated the design of LSST. But of course, what we really will find, we don't know yet. And that's really one of the most exciting things. Okay, so now I'm going to talk a little bit about survey operations. And just so that you have like a real personal feeling about this, we sent Phil to La Serena to tell us about it. So I'm going to stop sharing screen. So actually, I have one more slide. We're going to go to La Serena. Phil is there. He's our senior correspondent. He's live from Rubin, the base facility, and he will take us on a tour. Let me here. How do I do this? I undo. All right, cool. Phil, you're on. Are you there?
All right, thanks very much, Chihway. Yep, I can hear you have the earpiece in. All right, well, thanks very much, Chihway. Very nice to see you. I did take a look around the auditorium. So many familiar faces. It's good to see one again. So yeah, sorry I can't be with you in person this week. But we figured that the next best thing, or as Pat put it, an even better thing than having me there in Stanford with you is to have me here in Chile. So there's very few places, I think, in the world that can compare with KIPAC in terms of how much fun it is to do science there. But Rubin Observatory is one of them. And so here we are in the base facility control room. So we're not on top of the mountain here. This is down in La Serena by the sea. But I'm sitting here in the remote control room, very similar actually to the control room that we're putting together at SLAC on the first floor of the Kavli building. So you should ask Tony Johnson about that if you bump into him at coffee. But here you can see we're all set up for tonight's observing run. The auxiliary telescope is on sky tonight. And so the observing specialists will be doing some imaging, also some calibration spectroscopy. The imaging is interesting. They're already 2 years away from survey start, but observing using the LSST scheduler. So they're taking images every 30 seconds in the same way that we'll take visits. It's all scripted. They're solving problems. They're documenting, doing the things that the observing specialists will at night during the survey. So it's quite nice to be up to speed already there. Just being here this week, there's a number of KIPAC folks here. Kevin Reel is resident already as the observatory scientist. We have a couple of observing specialists on the staff. Yijun Kang is here already, and Shuang Liang, who I think might be in the audience there. He's going to come down to Chile in the coming months. Please do watch out for Kevin Fanning as well, who just joined the team. He's going to be moving down in October. So plenty of people from KIPAC coming through, and you can really feel the influence down here. So I wanted to say a few things about Rubin and KIPAC before giving you some information about not just the survey that we're planning, but the data releases that will be coming out for people to do science with. But before I get there, you heard a little bit about how long I've been at KIPAC. I've actually been in Rubin LSST for as long. I showed up in 2003, and almost straight away, Steve and Roger sold me on working on preparing for science with LSST. I looked it up. Back then, we imagined the survey would start in 2011. We've made progress since then. Then by the time of KIPAC at 10, we'd become a real project. Rubin was a real project. And then we thought, well, first light was planned for 2019, and we'd have 2 years of commissioning after that. So we're not so far away from that, but the pandemic did get in the way, and so we've been delayed by that. So I'll come back in a minute when we start showing slides again. I'll show you where we're at with the Rubin schedule. Just to say, though, while I have the chance, I am very grateful for these 20 years of opportunities with both KIPAC and Rubin. It's dawned on me over time that this has been a huge opportunity to be part of something really big. That is to say, big science with big data in big collaborations. And over the last few years in particular, it's been the opportunity to try something new. So I came to think about strong gravitational lensing analysis, and then ended up staying for things like collaboration, leadership, and operations planning and management, and things that I didn't think that I would end up doing. But turns out they are interesting ways to be a scientist at ever increasing scale. And so that's been fun to think about. Fun things you might think about out there in the auditorium audience are the possibility to join the commissioning team and help out if you're at KIPAC now. And there's even ways to get involved and help out by bidding to be an in-kind contributor. You might hear more of that in the next few weeks, but certainly still lots of good ways to get involved with Rubin and help make this amazing thing work. In terms of science, what am I excited about? Well, definitely still keen on doing the strong lensing analysis. But in general, I think the thing I'm most excited about with Rubin is the way that it's going to give everybody a big data problem, where by definition, big data means you have to fundamentally shift the way you think about your analysis. So you saw how Greg tackled a big data problem of his own with the amazing Gaia data. There's going to be astrophysicists everywhere trying to get to grips with the LSST data, and it's going to be great fun to see what everyone does. In terms of locally, I wanted to show you a little bit about the Rubin Science Platform, which is one way to help people cope with their big data problems. It's take them and enable them to work where the data is rather than them bringing the data where they are. And then at KIPAC, close to home, we're trying to solve our own personal strong lensing big data problem using neural posterior estimation, which is something that Yashar and Laurence bequeathed us as they left for Montreal. So yeah, I don't have slides on this, but if you get a chance to chat with Sydney Erickson in the audience, also Padma Venkatraman and Phil Holloway, Aaron and Greg and others who are meeting every week to think about strong lensing analysis. We are now training deep neural networks on sets of 100,000 or 500,000 synthetic gravitational lens images so that we can do very fast approximate inference. So enabling us to analyze test sets of up to 100,000 LSST lens systems within a standard one-day development cycle. And this was inconceivable to me back in 2003. And it's kind of amazing that we now have the tools to be able to do these things at LSST scale. Now, I think, Chihway, we might be ready to share slides again, and I can say a little bit more about the Rubin Science Platform. Are you there, back in the studio?
Thanks, Phil. We're going to move you off screen, and we're going to continue with... Are we sharing? Yeah, I think we're sharing.
Yeah, I see it. All right, good. So would you mind doing that thing, you know, where I say next slide, please, and you do it? That would be great.
Yeah, can do. Go ahead.
Okay, so here's a one-slide summary of the data products that we're going to be providing from Rubin, and also the tools to use them with. So a lot of information on this slide, but have in mind prompt data products, that is coming out every night, a stream of alerts where something has changed in the night sky, and then a database of prompt products to go look things up in once you've studied the alerts. And then every year we'll put out an annual data release where each year we reprocess all of the images taken to date and remake all the catalogs of stars and galaxies, asteroids, and so on, and make an increasingly deep COAD image of the whole of the southern sky. And these data will be available to everyone in the LSST science community. That's up to 10,000 scientists across the world via this Rubin Science Platform, which is managed as part of the US data facility at SLAC. So next slide, please. Yeah, so here's one of the most fun things I've seen at KIPAC in the last few years. Here's a little demo of the Rubin Science Platform that Professor Louise Edwards from Cal Poly did for us. She came up to visit she stayed with us for a couple months. And she was very active on the Rubin Science Platform with some data preview data, which I'll explain in a minute. But here's some screenshots of her Jupyter notebooks on the Rubin Science platform using LSST-like data. And then you can see in the screenshot in the top right-hand corner, here she is explaining to us at KIPAC how we should use the Rubin Science platform. So I thought this was a excellent KIPAC tea, one of the best I've been to. And it really showed how the science platform is an equalizer. It provides both the data and computing resources to analyze those data to the whole LSST science community. It's an amazing thing. Next slide, please. Okay, so data previews, what are these? Well, we're releasing a sequence of data releases that we're calling data previews. They're pre-survey data releases. And the idea is to help ourselves develop the capability to serve data to everybody, but also support the very broad LSST science community as it prepares to do LSST science. So there's 3 of these previews. DP0 it's now been released. It was a set of simulated LSST-like data products, basically to enable analysis verification tests. I'll show you a picture of what DP0 looks like in a sec. DP1 and DP2 are the real on-sky data from Rubin commissioning. So DP1 will be a small set of the first science grade images, roughly speaking, either taken with LSST cam or the single RAF ComCam commissioning camera, both of which are assembled here at SLAC. And then DP2 will be the set of LSST cam images taken from around 3 months on sky observations right before we start the survey. And you can look forward to things like a set of a few pointings that enable a 10 to 20 year depth test in 3 different fields. So very, very deep, but taken very quickly. So interestingly fast time sampling in that data set. You can also look forward to 1,000 square degrees in all 6 bands, UGRIZY, to about 1 or 2 year equivalent depth as something like an LSST pilot survey. So that DP2 data set it will be sort of similar in character to the DES-SV data. So those of you who remember that, it's the first big data set to really get your teeth into and do science. Next slide, please. So I thought it was worth spending a little bit of time on this. This is DP0.2, 300 square degree virtual Rubin sky survey. It was released last summer. It's still available on the science platform. Lots of people working on it. This was a reprocessing by us at Rubin of the LSST desks DC2 virtual sky survey IMSIM images. And so this was a nice collaboration between the two sides of the Rubin LSST HEP experiment, as we like to think of it. And so in the picture up here, you can see just a little snippet of what we all made together, which was something like visit and co-ed images in all 6 bands over these 300 square degrees for 5 years at the current, or at the time baseline time sampling frequency, the cadence. There are also different image analysis light curves for people looking to develop their time domain analysis. And I put here a list of all the people from KIPAC that are on the author list of the desk's DC2 paper. And it was pleasing to see that nearly 20% of the authors on this key survey paper came from KIPAC. We really did work a lot on it together, and it came out great. Okay, next slide, please. All right, so here's a slide for all of you who are thinking of putting in a 3-year research proposal this fall, either for an institutional fellowship or for NSF grant, for example, due in November. Here's how to think about the years 2025 to 2027, your next 3-year funding period if you apply this fall. Excitingly, these will include the first LSST data releases. So year 1 of your 3-year program will be about preparing for LSST science and taking a look at these DP1 kind of first look real images. And then in that year 1, the survey will start, you'll get the first alerts. In year 2 of your next grant period, you'll get to work with the DP2 science validation survey images from LSST cam. You'll be into the year 1 and year 2 alerts. And then at some point later on in that year, there'll be the first LSST data release, which is not an annual data release, it's the first 6 months of data. And then in year 3, for your big results that you're proposing for this fall, will be the starting the analysis of DR2, which is the year 1 data set from LSST. So just wanted to leave you with this thought that Chihway's very long wait for data is nearly over. Okay, back to you, Chihway, to finish off.
All right. Thanks, Phil. That was amazing, and thanks for taking us on a tour in La Serena. I know I can't beat the excitement of being in La Serena, but Phil has other things to do, so we're gonna continue here at KIPAC. Okay, so last bit I'm gonna talk about is stuff we're doing to prepare for this data that will come from LSST, like what Phil just showed. Okay, so just reiterate some of these numbers Phil showed in his previous slides. This is the data we're going to get. It is 20 terabytes per night, 60 petabytes in 10 years, 60 seconds from the imaging to the alert, 10 million alerts per night. So this is all very new territory in at least the astronomy cosmology community. And it is not like we can just sit here and wait for the data to come and then we will know how to do everything. There needs to be new infrastructure, new algorithms, and new ways of thinking if we really want to get the science that we thought we were going to do with this instrument. And to prepare for that, there's these science collaborations that surround Rubin that stood up. One of them is the Dark Energy Science Collaboration that we talked about. We are one of 8 science collaborations, and basically we study everything dark energy related. So galaxy clusters, supernova, type 1A supernova, I just said that, sorry, strong lensing, large scale structure, weak lensing. I'm going to focus on weak lensing because that's what I know about, but you can trivially kind of extrapolate to other areas where other people are kind of preparing in a similar way. Okay, so one word about weak lensing, just so everybody is on the same ground. So weak gravitational lensing refers to when you have galaxies, distant galaxies, and the light travels from there to us. The light rays are going to get perturbed slightly because of the gravitational potential being perturbed by dark matter blobs along the way. So that means that when we have a distant galaxy that is circular, like what is shown up there, it might appear elliptical when you see it on your camera. And that influence is encoding the matter distribution through the universe, or the skeleton structure of the universe. Okay, so that's weak lensing. That means that the main observables we have is these distorted galaxy shapes. So that's one ingredient. We need to know how far these galaxies are, because that is how much matter there is between them and us. And then we need to have a model to connect this all together. Given these observables, what is the inferred kind of cosmological model that describes the dark matter distribution from the galaxy to us? Okay, so here are kind of the main ingredients that basically consist of doing a weak lensing analysis. Later on, I'm going to highlight KIPAC members that contribute to the different elements that I just showed. But I want, before that, to talk a little bit about history again. And just to note that this whole field of using weak lensing to infer cosmology is actually also about 20 years old. What a coincidence. So 20 years of cosmic shear from the first detection in year 2000. That's a first detection of the signal by 4 simultaneous kind of experiments using about 100,000 galaxies. There's been a series of analyses after that where people basically found the same signal in existing data. But the real kind of coherent effort in trying to do a cosmology analysis from a coherent data set came around 2013. So there's kind of a bunch of experiments that happened around then. Simultaneously, there's been new experiments being proposed. You might have heard of Dark Energy Survey, the Hypersur Prime Cam, the Kilodegree Survey, all started about 2014 or so, with the hope of using a new camera and an old telescope to get this signal measured more precisely. From 2014 to about today, you see all these kind of intermediate results from these big surveys coming out. And then looking forward, basically is the LSST era where we're going to blow this whole thing out of the water. Okay, so you can look at the surveys, and this year is basically the year of the paper published. But you can also look at the number of galaxies in this timeline. So we started with 100,000 galaxies. Right around 2013, we reached the million marks. In this period, there was tens of millions. And DS year 3 is the first time we reached 100 million galaxies. LSST is going to come with billions of galaxies. So it's another order of magnitude jump in this time series. Okay, so cosmic shear as a science went from detection to something very mature, very mainstream, very complex in 20 years. So I think one of the main reasons this has been pretty successful is that it is really hard, but people have been able to solve the hard challenges throughout the years. So if you look at what people have been worrying about throughout the years, it's been changing. So we had a challenge, people invented new things, they solved it. So here's just a running list of things we used to worry about, we still worry about, but we kind of invented new things to solve these problems. New technology came along. So this kind of has been the story in the last 20 years. And I think if history is any guide, we can expect that in the age of LSST, we would come up with new challenges. But hopefully, we will also come up with ways to solve them. Okay, so with that, I'm going to go through a series of pretty quick highlights of these different challenges that we're facing currently in weak cleansing, that KIPAC members are involved in solving them or kind of studying them. I am going to highlight some people. It's probably very biased towards people I know and in my age group. So I apologize up front if I didn't do this complete, but I really tried. There is, I think, only one person out of all the people that is not a KIPAC affiliate. If you know of this person, I don't know, you can get my drink ticket on Thursday if this thing exists. But anyway, let's go on. Right. Okay, so the first person I want to highlight, not exactly recleansing kind of centric, but I think he's very important in this whole Rubin science connection. Keith Bechtel, he was in my same year. He is one of the main persons in the science commissioning and validation effort and connecting the telescope side with the science side. And I think people who in desk must all kind of know him. And I thought maybe you don't recognize him if he's not in his running shirts. So I put it up here. This is what he was known for when he was here as a student. And probably whenever he comes here, you still see him running like 7 a.m. Up the hills from campus. Okay, so that's Keith. The point spread function. So I'm going to go from kind of low level, pixel level up to high level cosmology. There's a lot of work here in trying to understand the kind of the response of the instrument in the atmosphere and how that imprints onto our shear measurements. And that sort of generally is in this group of point spread function. So I listed Pierre-François, Theo, Claire, Elise, Josh, who all really put in a lot of work in this area. This is just, I think, a picture from Josh showing the PSF distributions in the focal plane of LSST. And here's kind of the color-dependent PSF size in relation to the 6 LSST filter bands that we talked about earlier. Okay, so after you get the PSF modeled, you want to measure these shapes, right? We talked about earlier, that's one of the main observables. In the first like 15 years of the 20 years I talked about, it was all about measuring shapes. People came up with different algorithms, very sophisticated models, very sophisticated simulations. It's been a hard problem, although it seems fairly trivial. So one of the hardest things to get right is the absolute value of this quantity shear. You have to calibrate it to some crazy sub% level, and that has been the hardest thing. So around like 2000, I don't remember when, this new idea came about that was pioneered by Aaron, Matt, as well as Eric Huff and Rachel Mandelbaum, where you can actually get this calibration from the data itself. And this kind of general idea is called meta-calibration. So that kind of went on and became this whole industry of you can also calibrate the detection from the data itself and many other things. So that kind of is this body of work where now the newer generations, such as Sid, who is here, that's carrying on and understanding it even deeper for LSST. Okay, so blending. So this is about, we talked about we have a lot of galaxies, right? But the size of the sky hasn't changed. So really we're saying the galaxies might get so dense that they'll overlap. And when the galaxies overlap, they will start to cause problems in photometry and photoses and many other things amongst shape measurements. So Pat, together with her group, has like put in a lot of work in trying to understand the effect of blending and how it propagates downstream into cosmology. Somi is one of the recent graduates that did work in such area. So this is basically one of the examples where you can show the Rubin pipeline, try to deblend two blended galaxies shown in the red cross, not being able to, it identified as one. And here's kind of the residual of that model. So yes, a lot of work done here. It's going to be a pretty uniquely LSST problem because we haven't had such good data before. Redshifts. So this is about how far the galaxies are. We talked about earlier, right? So LSST is not going to be a spectroscopic survey, which means that we're using 6 numbers just from the photometric bands to know where how far the galaxies are. And if you just think about that, that's kind of crazy, right? How would you even do that? So fortunately, we don't need to know individual galaxies, how far they are, but rather kind of a sample of galaxies where they are. There's been a lot of work here, kind of pioneered by Daniel, but also carried on by Alex and Justin, to understand how to rigorously, in a rigorous framework, quantify how the redshift distribution is given the spectroscopic training set we have. So this is kind of indicated by this picture showing a self-organizing map of the DES galaxies. This whole framework, we think, will also get pushed on to LSST. Eric Charles is one of the main persons that are working on the LSST infrastructure to do such work in the desk kind of environment. So lots of work in the redshift area. Also lots of work in just modeling this connection between galaxy shapes and cosmology. So there's a lot of work led by Elizabeth on kind of the DES year 3 cosmology work, how you model different effects in both weak lensing and galaxy clustering. I also wanted to highlight Anya's and Jesse's recent work on exploring beyond lambda CDM, what our data is actually telling us. I especially want to highlight Jessie, who is in the audience, is an amazing artist. So she has this series of science-inspired illustrations. This particular one is showing lambda CDM fighting over these 6-headed monster of alternative models. And yeah, check it out, #DarkBytes. There is a lot of amazing art from Jessie. Okay, so moving on, one of the main tasks for desk is actually to synthesize, digest, and understand what happened with the current surveys, right? DES, KIDS, HSC, they're all coming to an end. And what did they find and what can we learn from it to go forward? So one of the works that we've done here is to reanalyze all of this work with a fresh eye, with new tools, and to see if the previous data sets are even consistent with each other and what that infers for kind of future for desk. So this is work led by Emily, who I believe was shortly here as well, and myself. Okay, so weak lensing is amazing, but some might say that it can do even more, or ultimately the calibration actually might come from some external sources, such as the CMB lensing. So this pioneered by Manu here, as well as Yukio Mori, who was also here there's this whole industry of combining weak lensing surveys with CMB lensing. So back in 2016, Manu told us that, you know what, shear calibration is hard, but CMB lensing is going to solve it for you. And then we went ahead and tried to do that in DES and SVT. So there's a whole new kind of area that is kind of coming up to getting popular. I say right about now, where we also have these big CMB experiments coming online that you will also hear about, I think, later today. Okay, so that is my quick rundown of KIPACers and weak lensing and cosmology in general. So lots has happened, as you see. I missed a lot, but there's going to be continuing to be more young people coming up and doing science in this area. Just to come back this theme again, what we're really going to find may not be the thing we thought we were going to find. And I think that's very exciting, and I'm really looking forward to it. So just leaving you with this kind of thought. And the last thing I think I'm going to say is, so the talk between me and Phil has been a little scattered, but this is exactly like what we're trying to do. So I've tried to kind of tell the story of, in the last 20 years, how these three things have been intertwined and cross-path and co-developing. So Rubin and LSST, obviously, weak lensing as a field and doing cosmology, and the KIPAC community and the wonderful people that are participating in this. I personally have been very lucky to join a little bit of this extremely exciting journey. This picture is KIPAC at 10 years when I was a grad student here. We made this chalk art outside the path where you can go see it later. We don't have it this time, but back then, I thought 10 years was long. There's still time. Okay, I'll do it later over coffee break. So back there I thought 10 years was long. Now I think 20 years is long. So I'm still looking forward to the next 20 years of excitement. Okay, so before I close, well, I have your attention. I'm going to advertise this. So as Manu said, KIPAC has a little baby sister called KICP, which is, as Aaron said, KIPAC spelled wrong. So this is Chicago. We're basically coming up in 20 years too next year. So you're welcome. I know a lot of people went by Chicago as well. So Chicago in summer, it's beautiful. Okay, so I'm going to close there. Happy to take questions, both me and Phil, and thank you for your attention.
Thank you so much. Questions for Chihway and Phil, please again, wait for the mic. And if you have questions online, use the Q&A button. Yep, Aaron.
Yeah.
So, sorry, Chihway, to put you on the spot, but so as you know, as we're approaching the start of LSST, what do you think we're going to find cosmology-wise? Do you have a personal point of view about what nature might have in store for us, if you're willing to share?
I don't. Okay, so I talk about weak lensing a lot, but I think like the first year or so of LSST weak lensing, it's not going to be too different from the end of stage 3, given the depth and everything. It's going to be wise, so a lot better statistics, but I think partially the newer thing, at least in the early stage, is going to be this transient domain, just because how we never had this data before. So I think it just in that aspect, I don't know what's going to happen, but I feel like that is an area that we might find surprises. In terms of more static science, I think it will come a little later when we build up enough depth that we started looking into places we haven't looked at. So I think that's going to be exciting. And of course, the thing we all want to get is the lambda CDM breaks. And then we get some new model that we are able to understand. So yeah, so I think that's what we want. Whatever can do that would be great. And yeah.
Thank you. Any other questions, Sandy?
What do you think are the biggest modeling or theory challenges in preparing for LSST and truly take advantage of the data?
Right. So that's a good question. So I don't know if you call this modeling challenges, but there's a lot of astrophysical kind of elements even in weak lensing, where we originally thought it was a very clean probe. Now we know that baryonic effects affects the small scale kind of matter power spectrum. We know that galaxies intrinsically are aligned in preferential ways because of a tidal field, and that contaminates our signal. So in general, if you look at the end of kind of stage 3 current surveys, that has been the limiting factor more than measuring shear. LSST is going to be different, we don't know, but I think those astrophysical challenges, we can no longer be these like pure cosmologists and saying we don't care about what galaxies are doing. What they're doing is going to be important, and I think solving that both is going to enable us to do what we want to do, and it actually will push us into areas that we weren't able to look at. Once we get the astrophysics sorted, we might be able to look at scales that are much smaller and get an additional way to test them to CDM and other things. So for me, that's I think my bet, but I'm sure other theorists will have other thoughts in the audience.
Yeah, but and then
you should also have questions for Phil.
Question for Phil. Hi, this is Pat. Hi. Do you know what's going on the mountaintop today? And will there be auxiliary telescope observing tonight? And what's the goal, if you know what it is?
I can tell you roughly, yes. This week there is an Orkstell observing run, and as far as I know, it's going ahead tonight. There's less happening in the day on the summit just this week, while they solve a particular problem that's causing some holdups. But the observing run is okay to go ahead. I'll be up there Thursday night, and tomorrow during the day as well. I'll be there observing the observing, so to speak. I think the Orkstell observing will be a mix of imaging and spectroscopy. One of the things they're doing is testing some new hardware that our French collaborators have arrived with and want to install. This is calibration equipment that Mark Meneers and his team have brought up. So he was there with us on Monday before going up the summit. So Orkstell is interesting for a number of reasons. One of them is it's a place to test things out before they're installed on the main Simone survey telescope. So that should be a lot of fun.
Chihway, you spoke a little bit, or you alluded towards the end a little bit to CMB playing a role in calibration and so forth. Let me ask, what do you see as the future of CMB and Rubin data together? Right. What are you most excited by?
Okay, cool. Okay, so originally I was really excited about what Manu showed in 2016, that we can calibrate shear with CMB lensing. But I think as we done this whole thing with DS and SPT, the level of the calibration is good, but the level we're able to calibrate the shears with other sources are even better. So at this particular point, that is not the thing I think that CMB will most likely come in and solve for us. However, I think it's coming on more and more that this thing we talked about, baryonic effects, are going to be a problem. And I think in that area, things like cross with TSC, KSC is going to be a very important thing. Now, I think we haven't really closed the loop in really figuring out how to do it. There's been measuring papers here and there showing that it constrains something, but really folding it back to do cosmology, I think that's hasn't been done in a mature way that we're all kind of on board and understand how to do it. And I think that's something I think is the most potentially interesting thing. You can push a little further and ask, when you do that, you might as well just throw CMB, TSC, KSC, lensing all together and do a joint analysis of the full thing. So I think that will be super exciting. It's a little bit far out there, but I'm sure by the time of S4, that might be achievable.
Great. And I'll just take this opportunity to advertise Bernie Reed-Guachaya, student here, whose thesis project is going to be to try to do exactly that.
Cool. I'm glad. Thank you for doing this.
Another question, Greg? Mike,
I guess this is for Phil. So can you say a little bit about what kind of data is going to be available to collaborators versus just everyone everywhere in the world? And on that same subject, is I think it was called the Rubin Science Platform. Is that available to sort of everyone everywhere, including non-collaborators? And finally, could you say something about the cadence, throughout the years of when data releases are going to happen?
Excellent. Okay, so the last one is easiest. We're aiming for annual data releases. So one per year, actually 2 in the first year, but then 1 per year after that through the 10-year survey. Okay, so you asked about collaborators, and so the way we think about data availability, Rubin, is more to do with data rights holders than collaborators, because we have these LSST science collaborations, but it turns out not everyone is in one. And so the LSST science community of people who will have access to the data after each annual data release, for example, that's the 10,000 people that I refer to, up to 10,000 people. It's every scientist in the US and Chile, plus a long list of scientists in various other countries around the world who have been making or are going to be making in-kind contributions in return for data rights. So those are the collaborators really that will get immediate access to the data release products, as well as access to the alert stream, which will be fully public. The alerts will come out from the US data facility. They'll get filtered by these broker systems, but the brokered alerts will also be public for anyone in the world to do astronomy. We do have the beginnings of a plan to make the LSST data available world publicly 2 years after each data release, and we'll be rolling that out in the next year or two. But for everybody who has LSST data rights, these special 10,000, we can think of them as one giant international collaboration. They'll all have the same data rights, the same access to the data, in the sense that they can get an account on the Rubin Science Platform and work with the data there. Did I get all 3 parts of your complicated question, Greg?
Yeah, thank you, Phil.
Another question from Phil. What do you think we will learn new from strong lensing? Can you say a few words? What new things we can learn? So
my hope and goal is that one of the things we learn from strong lensing is actually the same thing as the thing we learn about dark energy in general, because one of the real strengths of the LSST survey data set is that it does enable these different and distinct ways of measuring the dark energy parameters and other cosmological fundamental physics parameters. So, I mean, my work and others is all about trying to make strong lensing a competitive probe within that set of probes. And so I hope that we will learn from strong lensing in combination with the other probes something interesting about the universe. And I don't know if Steve is in the audience, but he always likes to say, if it's lambda CDM, that's just as interesting as if it's some different model for what's going on. Just because it's so weird, lambda CDM is so weird theoretically that it would be very interesting if that holds up. And so I'm trying to remain agnostic about the model. That's for Jessie. So she sees I don't have any experimental bias.
So another question for Phil. I see you sitting in front of lots of electronics equipment. So you talked a bit about, or quite a bit about the photonics part of it. What role the advancements in computers and memory technology and data storage are playing in your project?
So we are, right now, we are reusing a lot of HEP technology for doing things like moving data around and setting up workflows to do lots of processing. So we're using the Ruscio and Panda tools that the CERN experiments have put together. How those evolve over time is to be seen. In terms of the storage technology and the science platform technology, we're part of the shared data facility up at SLAC, which is the new and upcoming high throughput computing system. And there's a lot of work being done in Kubernetes containers with storage solutions set up for the kind of high throughput work we want to do. So we have a Weka file system, for example, and then we'll keep up with the technology collectively at SLAC to improve that system as we go. One thing at the moment is that the processing pipelines are all designed to run on CPUs. And this is, a decision made a while back, but you can think of the early part of the survey being just do the standard survey processing that we know how to do from dark energy survey and do it at scale. And we think we can do that. It'll be interesting to see how over the course of the survey, at what point do we really seriously move to GPUs, if at all, and what other things will come along to help us do the processing better and refine it and so on. I thought it was really interesting in the Fermi days how the systematic errors or the available precision even in the data changed over time. That they did better than root N because they were making improvements in the analysis. And I'm wondering whether something like that might be possible through for Rubin as well, through some combination of improved hardware, improved processing, improved analysis. It's going to be interesting to see. A lot can happen in 10 years in terms of making things better.
Great. Another question.
Yeah, there was a lot of talk about the light pollution from the fleets of satellites people put up. Is there still a... Do you want to say something about it?
I can say we're not as worried as we were when they first started going up. I mean, it was alarming when we first saw when we all first saw these strings of low Earth orbit satellites, especially after launch and at dusk, where they're very bright going across the sky. We're still doing the analysis to look at try and understand the subtle effects of these things, but just the basic contamination of having a bright streak across an image from one of these new satellites. It looks as though with current forecasts for how many thousands of these things will be actually in the sky, it looks like more of a nuisance than a problem. It's sort of around a few % of pixels lost over the course of the survey. And the way to address that is to just survey for longer to fill in that depth. There's some risk with new satellites going up that are not small and black, but instead bright and shiny, which could be, more of a problem. To its great credit, NSF is working on the regulatory landscape to try and keep the providers of these global internet systems try and keep them sensitive to the needs of optical astronomy, so that the light pollution, as you put it, doesn't get worse than we're already expecting. There's a interesting project being done this year actually to look at the more subtle effects of these low Earth orbit satellites going across the images. Once you've masked out the bright streak, there's still an issue of crosstalk and persistence and other effects further out from the streak. And the question is, well, what impact does that have on the correlated noise that might affect, for example, the weak lensing measurements? So far, I don't think there's a lot of concern about that within the desk. We'll see how the study comes out, but because of the way the images are combined, and we have so many images that can be combined, I think that's our main mitigation against the subtler effects of these satellite streaks.
Great, thanks a lot. And I have a few more questions for Chihway and Phil, but I think I'll have many opportunities to ask. So let's thank our speakers again for a nice talk.
Oh, and I should maybe advertise if I have 10 seconds.
Yes.
It's a lot of advertisement in this talk. All right, go ahead.
Yeah, this is a really good one though. Okay, so this is the base facility control room. We thought it would be fun if you're around Thursday morning first thing, we'll try and set up a summit tour for you. So I'll go and stand up by the telescope and show you that in real life for 15 minutes or something like that. So we'll try and do that at 9 a.m. on Thursday.